Welcome to the lecture 3. So here in this lecture we'll start talking about semiconductors. So physics of semiconductors. So we will first introduce semiconductor materials, what semiconductor materials are from a microscopic point of view. Then we'll talk about the bond model of semiconductors, which is a very simple model of semiconductors. We will talk about what intrinsic semiconductors are, what extrinsic semiconductors are, and what doping means, what n-type semiconductor means, and what p-type semiconductors mean. Alright, so we will use Pire as our reference. So what we will talk about today is mostly covered in chapter 2 section 2.2 in this textbook. Alright, so again we start with this cross-sectional image of a microprocessor chip, a digital IC, and in the previous lecture we talked about metals here, and this material here is oxide, and what we are going to talk about is what is actually in the bottom of this cross-section, semiconductors. And semiconductors is the most important part in any integrated circuits. So here we have a cross-sectional, a blown up image of a MOSFET, metal oxide semiconductor field effect transistors, and this material over here is the semiconductor. So let's look at another magnified image here. So here this region, this region over here is what is a semiconductor material is. So this is the semiconductor material in a MOSFET, metal oxide semiconductor field effect transistor, and then you have other components here in a MOSFET as well. So here you have an oxide material, and here you have another oxide material, and then these are the metal contacts. Alright, so just wanted to introduce semiconductor materials as it is in a transistor. So we will talk about transistor in more details in the later lectures. Okay, so semiconductors. So semiconductors in the periodic table, most of the popular semiconductors, most popular semiconductor is silicon, which is a group 4 material. So in the periodic table here we have silicon here, and also most of the other materials in the group 4 are also semiconductors. For example, germanium is also a popular semiconductor material. Alright, so let's look at the valence of a silicon. So silicon has an atomic number of 14. So it has 14, and so the electron distribution in its different levels is like this: 1s2, 2s2, 2p6, and 3s2, 3p6. And this 3s2, 3p6 is the outermost shell, and so there are 4 valence electrons in a silicon. So now note that in the n equals to 3 level, there are total 8 states. So this outermost shell is only half filled. So there are 8 states in the outermost shell, and it is filled with only 4 electrons. Now this is the crystal structure of silicon. So this is the unit cell of a crystal silicon, and what you see is that each of the silicon atoms forms a bond with 4 other silicon atoms here, and the way these bonds are formed, these bonds are covalent bond, and each of the silicon atom contributes 1 electron, such that there are 2 electrons in each of these covalent bonds. So again, silicon has these 4 electrons in its outermost shell, the 4 valence electrons, and it uses these 4 electrons to form 4 covalent bonds. So the silicon atom forms 4 covalent bonds with 4 nearest neighbors. Alright, so now let's talk about silicon crystal at absolute zero temperature, which means that 0 Kelvin. Now again, because silicon has 4 electrons in its outermost shell, and all of these 4 electrons are used up to create 4 covalent bonds with 4 nearest neighbors. So at T equals to 0, the absolute 0 temperature, a silicon crystal does not have any free carriers, meaning that all the electrons are used up to create these bonds. So at 0 Kelvin temperature, there are no free carriers in a silicon, and it behaves like an insulator at absolute 0 temperature. Now let's think about what happens if you increase the temperature. Now if you increase the temperature, what happens is that some of the bonds gets broken, and once some of the bonds get broken, it generates an electron and a hole. So it creates an electron here, and once it creates an electron, there is a vacancy in this bond which we call a hole. Okay, so this is a hole and this is an electron. Now electron has a negative charge, and you can think about a hole as a positive charge. Now the interesting thing is that it's understandable that the electron is free to move. What is interesting is the fact that a hole, although it's just a vacancy in this bond, this vacancy can also move. So basically, once a bond is broken, it creates a free electron and it creates another quasi particle that is hole, and that can also move like a particle and which has a positive charge, while an electron has a negative charge. So now if you apply an electric field, apply an electric field across a semiconductor in this direction, the electron will move in the opposite direction to the electric field, and the hole will move in the direction of the electric field. And note that for all practical purposes, we just consider hole as an equivalent of an electron, just that it has a positive charge. Okay, and the thing is, the movement of electron is opposite to the movement of holes. All right. Now another thing that to remember is that once at a finite temperature, when a bond breaks, it creates these electrons and holes. So you have a positive charge due to the hole and a negative charge due to the electron. So altogether, the semiconductor remains charge neutral, meaning that the breakage of the bond do not create a charged material. It remains charge neutral, just that it has equal number of electrons and equal number of holes. Alright, now let's try to see what is the atomic density of silicon and how many carriers are broken, how many bonds, what fraction of the total number of bonds are broken in pure silicon. So again, this is the unit cell of a silicon crystal, and the if you look at this cube here, the cube has a side of around 5 angstrom. Now let's calculate how many atoms are there inside this cube. So first you can see that there are 4 silicon atoms that lie completely inside of this cube. So here you have 1, 2, 3 and 4. So you have 4 silicon atoms sitting completely inside the cube. Then at the 8 corners, here, here, here and here, you have 8 silicon atoms sitting at 8 corners, and only 1/8 of these silicon atoms are inside the cube. So you have 1/8 contribution from each of the atoms towards the total number of atoms inside the cube. And then you have this, there are 6 atoms that are on the 6 faces of the unit cell. So you have this one over here, then this one, this one, this one, this one and this one. Total 6 atoms on the 6 sides, 6 faces of the cube. So you have 6 atoms, and only half of these atoms are inside the cube. So you have 6 multiplied by half. So the total number of atoms inside this unit cell of silicon is 4 plus 1 plus 3 equals equals 8. So there are total 8 atoms inside the unit cell of a silicon. So the atomic density is 8 divided by a cube. So 8 divided by a cube is the number of atoms per unit volume, which we call the atomic density, and this comes out to be 5 multiplied with 10 power 28 per meter cube. So this is the total number of atoms per unit volume of a silicon crystal. Now if each atom forms 4 bonds, the order of magnitude of total number of bonds per unit volume is around 10 power 29. Okay, now at room temperature, if you calculate the free carrier density, it comes out to be around 10 power 16 per meter cube. So note that the total number of bonds is of the order of 10 power 23, while the total number of free carriers is 10 power 16. So what you can see is that 10 power 29 divided by 10 power 16 roughly gives you 10 power 23, 10 power 13, which essentially means that at room temperature only one bond out of 10 power 20, 10 power 13 is broken in silicon. In other words, so again the free carrier density is of the order of 10 power 16 per meter cube, while the total number of bond density, the total bond density is of the order of 10 power 29 per meter cube, which means that only 1 out of 10 power 13 bonds are broken at room temperature in silicon. So this is an interesting observation, so interesting fact to remember about intrinsic semiconductor. Alright, so now let's look at what happens in an extrinsic semiconductor. So extrinsic semiconductor means that in a semiconductor, for example in silicon, you introduce some impurities. So the impurities can be group 5 or group 3 material, and this process of introducing the impurities is called doping. Alright, so again, silicon, for example, is group 4 material. Let's see what happens first when we introduced a group 5 material, for example, phosphorus. Now, as we have already seen, silicon has 4 valence electrons, 4 electrons in the outermost shell, where phosphorus has 5 electrons in its outermost shell. Alright, so here what we are seeing is showing here is a crystal lattice of silicon where one of the silicon atom is replaced by a phosphorus atom. Now again, phosphorus has 5 electrons in its outermost shell, so it uses 4 of them to create 4 covalent bonds with 4 neighboring silicon atoms. Now these 4 electrons in these 4 covalent bonds are localized, so they do not participate in the conduction process. These 4 covalent bonds, electrons in 4 covalent bonds, but it has 5 electrons in its outermost shell, so 1 is left and this electron is free. This electron is delocalized, and as a result this electron can participate in the conduction process. So basically it means that if you apply an electric field in this direction, this electron can move in the other direction. Now as you can see that each phosphorus atom will give 1 extra electron in the semiconductor to the semiconductor. So if the density of this dopant is Nd, so if the number of phosphorus atoms you have put into the semiconductor is Nd per unit volume, then the total number of extra electrons that you will have in the semiconductor will be Nd per unit volume. In other words, the electron density that you will have in the semiconductor will be equal to the dopant density. Now these group 5 dopants are called donors because they donate an electron to the semiconductor. Now one thing to note here is that although you are introducing electrons, it does not mean that semiconductor has become charged overall. The semiconductor still remains charge neutral after doping it with a dopant, for example phosphorus. The reason is that although it's giving an electron here, this electron, so the total number of electrons is equal to the total number of protons in this phosphorus. So although it gives out an extra electron to the semiconductor, each phosphorus atom has a corresponding proton in its nucleus, and as a result the semiconductor remains charge neutral even after the addition of a dopant, for example a donor atom like a donor species like phosphorus. So now let's look at what happens when you dope the semiconductor with a group 3 material, for example boron. Now in its boron is group 3, so it has 3 electrons in its outermost shell. Now what happens when you dope a material with a group 3 material is very interesting. So here again there is one boron atom that replaces a silicon atom in this lattice. Now as you can understand, this boron atom will create 4 covalent bonds with 4 of its neighboring silicon atoms. But note that it has only 3 electrons in the outermost shell. So what will happen is that one of the bonds in a neighboring covalent bond will break to create this bond. And what is interesting is that this bond will break to give it an electron to this covalent bond. But the thing is that this bond will also break at some point to give an extra electron to another boron bond with silicon somewhere else. So essentially what will happen is that these bonds will keep on breaking at a certain rate, which essentially creates a free moving hole in the system. So this idea is not straightforward the way we are explaining, but essentially what will happen is that this constant breaking of bond and then creation of the bond, the breakage of the bond creates an electron which goes into another bond, fill up another bond, creates effectively a hole in the system. So if you replace if you introduce boron into the silicon, each boron atom will create an extra hole in the system, and this hole again participates in the conduction process, meaning that if you apply an electric field in this direction, effectively this hole will move in the direction of the electric field, and a hole is opposite to of an electron, so which means that it has a positive charge. Now because this boron, because it has 3 electrons, effectively accepts an electron from a neighboring bond, covalent bond, and that's why it's called an acceptor. So group 3 material used as a dopant in silicon is essentially an acceptor. All right, to summarize, we have seen that there are 2 kinds of dopants: donors, which are group 5 materials, and this creates extra mobile electrons in the semiconductor, and this type of semiconductor, when doped with donors or group 5 elements, are called n-type semiconductors. On the other hand, when they are doped with acceptors, which are group 3, it creates more mobile holes than electrons, and then it is called a p-type semiconductor. And one important thing to remember is that both n-type extrinsic semiconductor and p-type extrinsic semiconductor are both charge neutral, because even the dopant species are charge neutral because they have equal number of electrons and protons, and as a result, even though both type of extrinsic semiconductors have excess electrons or excess more electrons than holes or more holes than electrons, overall the material system remains charge neutral. All right. Now let's end this lecture with an estimate as to what is a reasonable number of dopants in a semiconductor, on the higher side though. So as we have seen, the atomic density in silicon is 10 power 28 per meter cube, and the intrinsic free carrier density is 10 power 16. Now in reality what happens is that you cannot dope it to the same level as that of the atomic density. Usually the dopant density is of the order of, at max it can be 0.1% of the atomic density of the semiconductor material. In silicon, 10 power 5 into 10 power 28. So usually the highest amount of dopant that you can introduce into semiconductor is of the order of 5 into 10 power 25 per meter cube. Typically you dope a semiconductor material with a density of 10 power 21 to 5 multiplied with 10 power 24 per meter cube. All right.